Welcome to this lecture series in group theory. In today's lecture, we will look at matrix groups, which are very close cousins of linear groups. And let us recall a little bit. So if V is any vector space over a field F, then we defined the general linear group of V as the set of all the invertible linear endomorphisms of V, where the group operation was just the composition of the linear maps. And we looked at the special linear group, the orthogonal group if V is a real inner product space, and the special orthogonal group under the same hypothesis. So let me not recall their definitions. In today's lecture, we will define matrix groups, and in literature, you might not even see any difference between what I call linear groups and what I'm going to define as matrix groups. But in my mind, there is a difference, and I would like for all of us to appreciate the subtle difference, if at all. All right, so let's proceed. Some problems for practice. And now let us get started. So the general linear group of matrices we are going to define. Fix any natural number n and the field F. Then define the general linear group, or for the moment, let us not call it a group because we have to prove that it is a group. So what is this set? This set is the set of all the n cross n invertible matrices. How do I write this? Let me write it in words. The set of all the invertible n cross n matrices over F. So it's a well-defined set, and we define the special linear, or whatever this is. Right now I don't want to call it a group. We define this as all those matrices in GL and F which have determinant 1. Okay, so these are two sets, but if you equip them with matrix multiplication, so this is a set, and multiplication of the usual multiplication of matrices is a binary operation on it, because the product of two invertible matrices, both of size n cross n, is another matrix of size n cross n which is also invertible. So the usual matrix multiplication is a binary operation on this guy, and this becomes a group under that binary operation because the associativity is clear, because matrix multiplication is associative. The existence of identity, well, the identity matrix serves as the identity of this guy, and inverses, well, all the invertible matrices can be inverted. That's where the name comes from. And the inverse of an n cross n invertible matrix will also be an n cross n invertible matrix. So this is a group, and you can write down the details if you like. And similarly, this is also a group because, first of all, the matrix multiplication is a binary operation on it, simply because if M1 and M2 have determinant 1, both are n cross n matrices, then their matrix product also has determinant 1, because determinant of the product is product of determinants. And all the other steps to verify that this is a group can be checked by you. So these are groups, but then, well, what is the name of this guy? This is the general linear group, and this is the special linear group, and we have seen these names before, so why am I repeating them? Well, there is a small difference between this notation and that notation. The previous rendition of the general linear prefix was applicable to vector spaces, right? So GL of a vector space was the set of all the linear endomorphisms which were invertible under composition. This time, this n is in the subscript, and F is the sort of the input to this particular prefix. And this time, this is the set of all the n cross n invertible matrices. Here we were collecting endomorphisms which were invertible. This time we are collecting matrices which are invertible. And many times people do not distinguish between these two things, but there is a difference. A linear map is not a matrix. You can get a matrix out of a linear map after you have chosen a basis, but a linear map in and of itself is certainly not a matrix. So there is a very simple connection between the two, and this connection will be later fortified when we study the notion of an isomorphism. But for now, from GLF to the end to GLNF, there is a very nice and natural map which takes an invertible endomorphism as input, and outputs its matrix with respect to the standard basis. So when I write mat T, I mean the matrix of T with respect to the standard basis. Coordinate spaces have a standard basis, right? So let me not repeat all of that. So that is the connection between the two, and under this bijection, this is a bijection in some sense, which we will see later when we study isomorphisms. This and that are exactly the same objects. So in that sense, you may not distinguish them. Group theoretically, they are exactly the same, but in my opinion, there is a subtle and important difference which we should appreciate. All right, so we have these two examples of matrix groups. There are other matrix groups which we will see in this lecture subsequently. Before we get there, let's look at one simple example. So we claim that if Q is if this is a finite field of size Q is some natural number, and suppose you have a finite field of size Q, we previously stated that the only Q's for which you can find a finite field of size Q are prime powers. That's a different story, but right now Q is some natural number, and suppose you are able to find a finite field of that size, and you have a natural number n, then the size of GL and FQ is this horrible thing. Right? This is just an exercise. You should do it yourself, but let me still give the full argument, or at least the main steps of the argument. So the point is, suppose we have a matrix, and let's try to see when is it invertible. Let's try to build an invertible matrix where the entries are coming from FQ. And the way to do it is, if you know your linear algebra, all you need to do, exactly what you need to do is put n linearly independent vectors in their coordinate representation row-wise. You can also do column-wise, but I'm doing row-wise. So you pick a vector in FQ to the n. It will look something like V1. I mean, it will look exactly like V1 up to Vn, where Vi's are elements of FQ. And for each vector, you can think of it like, laid out as just elements of FQ in a sequence of n elements. So what do we need to do? We need to put vector V1 here laid out in its coordinate form, V2 up to Vn, such that they are linearly independent, and this is exactly the only, this is exactly the way to build an invertible matrix of size n cross n over FQ. So this problem of finding the size of this guy is exactly the problem of finding n linearly independent vectors. How many such lists are available where each where V1 up to Vn are linearly independent, and where the sequence matters, the order here matters. So once you realize that, in the first row, what you can do is pick any non-zero vector. For the first row, to fill up the first row, just pick any non-zero vector and then fill up the row according to the entries of that vector. And there are so many choices for it. There are a total of Q to the n vectors in SQ to the n, this particular vector space, but you cannot pick the zero vector because otherwise there is no chance of them being linearly independent. So except for the zero vector, you can fill whatever you want. So there are so many choices here. After you have filled the first row, now to fill the second row, you have to choose something that is linearly independent of the previous one. How many vectors are dependent on V1? The vectors which lie on the span of V1. And how many vectors lie in span of V1? Since V1 is non-zero, there are exactly mod FQ many vectors which lie in the span of V1, which is Q. So except for these Q vectors, you can pick whatever you want. And there are so many choices for it. And you repeat that reasoning once you've filled the first row and the second row. Now in the third row, you cannot choose anything in the span of V1 and V2. There are Q square many things in the span of V1 and V2. So in the third row, you have so many choices available to you. And if you just carry this out in full, you will see that the size of this guy is that much. So I didn't write anything, but I hope I have explained it well enough for you to be able to fill all the details fully rigorously if you like. All right, great. And just so that we have a concrete example on our hands, if we choose our field to be F2, F2 is the field with two elements, 0 and 1, as we write them. So we are saying that GL2 F2 is precisely this set of matrices. Of course, the 1 refers here to the 1 of the field F2, not the usual 1. And there are 6 different things written over here, and we already know that the size of this guy is 6 by using that formula. So this is exactly GL2 F2, and that's very nice. All right. Another important or interesting class of matrix groups is the set of unitriangular matrices. Suppose F is any field and N is again a natural number, then we can define this notation to be equal to this set, where what is this set? This is all the n cross n matrices. So these are, I should have said that these are n cross n matrices. Let me just put n cross n here to denote that. So all n cross n matrices of a particular form. On the diagonal we have 1, where of course 1 refers to the multiplicative identity of the field. Below the diagonal we have 0, identically everywhere 0. And above the diagonal, complete freedom. So those matrices, if you collect, that set is called or denoted by this notation. And note that this is also a group under matrix multiplication. Now this is not as easy as verifying the GLNF and SLNF business, but the fact that matrix multiplication is indeed a binary operation on it is not so hard to check. You just have to multiply two matrices of this sort and see that the diagonal entries will remain 1. So that's a very simple matrix multiplication exercise. So matrix multiplication is indeed a binary operation on this. The interesting thing to check here is the inverses. If you take the inverse of such a matrix, it will still be a matrix of exactly this form. Of course, the entries on the, above the diagonal will change after you take the inverse. But the point is the diagonal entries will still be 1, all of them. And the entries below the diagonal will still be 0. And that's an exercise in linear algebra. So if you face any trouble there, you can write in the comments. I do not want to do that exercise. So just verify that this is indeed a group. That much linear algebra you should know. Okay? And you can Google around also. It's not a difficult argument at all. Fine. So this is a nice example of a group. In particular, if you take n is equal to 1, you get this set. Right? UT1F would be this set. And interestingly, if you multiply two things from UT1F, if X is the entry here and Y is the entry there, the multiplication is this guy. So really what is happening is, this is basically mimicking the addition that is there over the base field. So UT1F is doing nothing new. You could have easily obtained UT1F in some sense just by asking for this object. It's just a decorated way of looking at the base field under its addition, right? Because the matrix multiplication essentially just encodes the addition in the base field. So I just wanted to mention this. This notion or this observation will be more formally stated when we discuss isomorphisms. All right. And one special instance of unitriangular matrices is the Heisenberg group. This is called the Heisenberg group because it has some connection with the Heisenberg uncertainty principle, which I'm not aware of what is the connection, but it does have a connection. This was discovered by Hermann Weyl, if I'm not wrong. So what is the definition? If F is a field, then we define the set H of F as such matrices. Unitriangular matrices of size 3 cross 3 over F. So this is exactly UT3F. Nothing more, nothing less. Okay, and let me just show you how the matrix multiplication here looks like. If you multiply two such things, you of course get something of the same sort as the previous slide already discusses. The entries will look like this. So they are not very simple. What should I say? The formula is a little complicated. And if you take inverses, it looks something like this, right? So you can just pause and see them. Best is to actually carry out this multiplication by yourself. So here we also see that using this formula, you can give R3 a very nice or very strange group structure. Because you can just, whatever are the entries of R3, you can put them here. The three entries, you can put them here. And then you can define multiplication of three entries of R3 by using this matrix multiplication. I hope that makes sense. So you can define a nice group structure on R3, though that is difficult to understand. Maybe you should write a code and see how that multiplication behaves. It would be nice to see. Perhaps I should also do that exercise. Okay, so with that, I want to end this lecture. As usual, I don't want to end this lecture. I want to discuss one very interesting puzzle now. Yeah, so this is a nice puzzle. It's a quirky puzzle. I don't know if it has any applications. If it does, very nice. But for now, it's just some Olympiad style puzzle, if you like, although it's not very hard. Fix a finite subset of GLNR, or rather, fix some subgroup. Okay, I don't want to say subgroup. Fix a subset of GLNR, which is finite and happens to be a group under matrix multiplication. So what are we saying? Fix a subset of GLNR, which is closed under matrix multiplication, so that you can at least talk about a binary operation on it. So the binary operation on this guy is the matrix multiplication, and for it to be a binary operation to begin with, this thing should be closed under matrix multiplication, meaning if you pick two matrices in G and multiply them, you will again get something in G. So fix such a subset and assume that it is finite, and further assume that this becomes a group under matrix multiplication. On the side, let me just mention that the finitude of G, assume G is finite and assume that it is closed under matrix multiplication. This is sufficient to guarantee that G will be a group, and that you can take as an exercise also. But for the moment, assume that it is finite, it is closed under matrix multiplication, and that it is a group under matrix multiplication, even though the third thing follows from the first two assumptions. Okay, now we want to show that determinant of M is Z for this particular M. So now what is this? Well, every G is an element in capital G, so it is a matrix. It is an n cross n matrix over R. Okay, and matrix can be added, and we are just adding all the matrices here. So this is not product. The group operation is product, but here we are adding things. Matrices can be added also. So this matrix is not necessarily going to be an element of G. This is just a matrix lying in GLNR. Not even GLNR. This is a matrix in MNR. MNR is the set of all n cross n matrices. As of now, this is a matrix just in MNR. We don't know. Maybe its determinant is 0. Who knows? So the point, or the puzzle asks you to show that determinant of that matrix is necessarily an integer. It's a quirky puzzle. I don't know, but it's the reasoning is interesting. That's why I'm discussing this. So you should pause the video and try to think about it. Yeah. So we have M is equal to this thing, and the main idea is to square M. Suppose you square M, then you get this equation, which we may write like this, right? And this implies that M square is equal to that. But concentrate on this particular sum. What are all these entries? GH with H varying in the group. What are these entries? This is exactly the elements of the group. This set is same as G. So using the fact, and this is just basic group theory, this has nothing to do with matrices. For any group G, recall, let me write it down, recall, if G is a group, then G is a group and you have an arbitrary element G in G, then this set, this is same as the set G. Okay, this we saw earlier at some point, and if you forget, doesn't matter, just prove it. It's very simple. So what is this sum? This sum is same as M, because the elements that you see here, they are same as the elements of G, just perhaps written in a permuted order, whatever order in which you wrote them here, even though the order doesn't matter because the addition of matrices is commutative, so in some sense there is no order. But whatever, I'm sure you understand that this is equal to m by using this particular fact. So this is equal to m, and that implies that we have this equation, because m will be added to itself mod g many times. So we have this equation. And now, well, you can, yeah, I'm also confused. Does this show that m is mod g times identity? Because you can just, no, you can't. So yeah, so if we knew that m were invertible, then we could just cancel m from both sides and would have said that m is mod g, and we would be done. So yeah, so we have to make two cases. Case one is that m is invertible. And case two is that m is not invertible. Or maybe, in fact, instead of making these cases, I would like to make two cases where determinant of m is 0, and the other is, it's the same thing as I wrote earlier, but I just am writing it in a different way. The second is that determinant is non-zero. In the first case, we are done because determinant is then therefore an integer. So here we are clearly done. And in the second case, you can just cancel m off, because if determinant is non-zero, m is invertible, so you can cancel off, and hence we find that m is actually mod g times identity matrix. So we have proven a little more than what was demanded of us. We just wanted to show that determinant is an integer, but we are ending up showing that it is either 0 or is equal to mod g times identity. So yeah, I mean, nice. I like the reasoning. I don't know if this will ever be used anywhere. I hope it does. Anyway, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.